All right, so what we're going to take a look at now is a much simpler way of defining state machines that doesn't involve a centralized location where you define the transitions between different states. So we looked at a way of defining transitions in a single dictionary, which kind of defines all the starting states, the triggers, as well as where you end up with, but you can avoid that completely. So we're going to look at a simpler scenario. We're going to model a combination lock, and that combination lock is going to be in one of three different states. So we're going to have a state locked, that's when the combination lock is actually locked. We're going to have the state failed, that's when you enter an incorrect code, and so we should print fail on the screen. And then the unlocked state, that's where you enter the correct code and the combination lock is actually open. So what I'm going to do here is I'm going to define, first of all, the code that opens the lock. I'm also going to define the initial state. So let's call this state locked. And then I'm going to define the entry. Now, the entry is going to be a sequence of digits that the user has tried to enter as they are actually opening the lock. So I'm going to have a string builder modeling this particular thing. So we're going to have a string builder like so. And then what I'm going to do is I'm going to build a state machine, but I'm going to do it differently. I'm going to make an infinite loop. So it's going to be a while true. And inside that loop, I'll have a switch on the state. So we're going to handle each one of the states right inside this loop. So I'll generate the different labels here. Now, we don't really need the argument out of range exception because we know we are limited by the three possible states defined here. And so let's actually implement them. I'm going to begin by implementing the failed state. That's when you enter an incorrect code. And so the lock tells you that you have failed, but maybe the lock allows you to type in stuff once again. So let's actually, first of all, right line the word failed. I'm going to make the word erase whatever the user has actually entered. So I'm going to say console.cursor left equals 0 here. So I'm going to go back to the start of the line, and then I'm going to overwrite the word failed over the actual digits that the user tried to enter. I'll clear the entry. So that's the entry that the user has been accumulating, the digits that were meant to open the code. And then I will set the state to state.locked. Okay, so after this, what happens is if you fail to enter the correct code, what happens is that we print failed, but then we clear the entry and set the state back to locked so you can try entering the code again. And this is the place where you would, for example, count the number of failed attempts and then correct them somehow. So in addition to this, let's implement the unlocked state. That's the good one. That's when you finally manage to unlock the whole thing. So once again, I'll say console.cursor left equals 0, console.writeLine equals, console.writeLine unlocked in this case, and I'm going to return from the program because, well, there's nothing else to demonstrate, is there? Now, the locked state is the one that's interesting because that's where we actually get the user's input. So we have this string builder called entry, which actually keeps every single digit. So we append to that entry the user's input. So we say console.readKey. So we read a single key without waiting for the line break for the carriage return to be entered. And we get the key char from that to actually put into the string builder. And then, of course, we can compare the string builder with the code. So if entry.toString is in fact equal to the code, then what we can do is we can say that the state is unlocked in this particular case and just break from here. Now, another case is we need to make sure that the user keeps entering the right digits. So if the code does not start with the string builder entry, that means the user has entered an incorrect digit, and so we set the state to failed. So we say state equals state.failed, and that's pretty much it. All right, so as you can see, we are in an infinite loop, which means that as the states switch from one to another, you keep coming back to checking every single state inside the switch statement and performing the appropriate calculation. So the program is actually done, and this is something that we can actually run right now and see what the output is. All right, so here we are. We have this input panel. Now, if I type 1, 2, 3, 1, notice it overwrites failed. If I type a 6, that writes failed once again. If I say 1, 2, 1, that says failed. But if I say 1, 2, 3, 4, it says unlocked, which is what we wanted in the first place. So the takeaway from this demonstration is that it's not always necessary to define the transitions in terms of some sort of dictionary or some sort of formalized structure, because in the case of a switch that you keep going through again and again and again, you can actually get the transitions as simple assignments here. Now, another thing that you can do, in addition to having an infinite loop like this, is you can actually jump from one case of the switch to another case of the switch. And this is also very interesting, because essentially what you can do at any location, like for example here the state is failed, and let's imagine there is no infinite loop. What you can do now is you can say something like the following. So instead of doing this, for example, you could say go to case state.failed, because guess what? C# allows you to jump from one switch case to another, and thereby you can orchestrate the entire state machine as a set of transitions from one switch case to another switch case, which is also very possible. Of course, it involves the use of the evil goto keyword, but I don't mind. I think that in this particular case, it might be warranted. And the upside of this implementation, as opposed to having a dictionary full of transitions, is you can do other things besides, and everything is kind of human readable. You have your case, the case is indented by 2 spaces, as you can see here, and in the case you can actually read what's going on, and you can sort of follow the code along instead of having to jump to some formalized structure that exists somewhere else. So it's certainly well and good to use formalized structures or indeed external frameworks, but if you have a very simple state machine like the one here, then perhaps having a switch is a more palatable, more understandable approach.